Hey guys, Mr. T here. This is another video. This one is on linear programming and also on the Simplex algorithm. So I should have probably added that to the title here. It's going to be in the file name anyway. So previously we've seen that given a set of constraints, we can make a feasible region, which is also known as a simplex. And we can, that simplex or that feasible region contains many possible solutions satisfying the constraints. Now, linear programming is the process of finding an optimal solution for a particular objective involving the variables in the set of constraints. So no longer are we satisfied with all of the possible solutions in the simplex. We're involved in a solution that meets a certain objective. So the objective is generally represented by a linear equation. In our topic, it's going to be linear equations that are of the objective. So some examples of that might be, the objective might be to maximize profits, therefore linear equation representing that objective would be representing the revenue. Another objective may be to minimize costs, therefore the linear equation representing would be representing costs in that case. The idea of linear programming can be summarized as, and this is straight from your book because I don't have any better way of explaining it, linear programming is a method for finding the optimal value, maximum or minimum, of a linear expression whose variables lay within a simplex. That linear expression is often called the objective function. So just add that to this. So the objective is a particular thing that we want to maximize or minimize, and it's generally linear. A generally linear equation, so we call it an objective function. Also note that, and this is where the simplex algorithm comes in, the optimal value of a linear expression over a simplex occurs at a vertex of this simplex. So the simplex algorithm basically states that if we set up a set of constraints and we've drawn a feasible region or a simplex, any objective function that we do is going to have an optimal value that's at a vertex of the simplex, which means that you'll find the maximum minimum values of an objective linear expression at the corner of a feasible region. It's not going to be in the middle. It's going to be at one of the corners of the feasible region that we constructed with the provided constraint. So let's have a look at a pretty complex problem here and break it down using techniques that we've done in the last few exercises. So two varieties of powdered food, Power Boost and Superlight, are used by athletes. So these are protein powders. Power Boost has 30 units of carbs, 30 units of protein, 100 units of vitamins. Superlight contains 10 units of carbs, 30 units of protein, 200 units of vitamins. Every week, athletes must consume at least 170 units of carbs, 1400 units of vitamins at least, but no more than 330 units of protein. Tins of Power Boost cost $5 each. Tins of Superlight cost $3 each. Tyson is an athlete who wants to satisfy his dietary needs but minimize his costs. Let X be the number of Power Boost tins and Y be the number of Superlight tins consumed weekly. And what is the objective here? So the only new thing that we need to do with this linear programming business is find Tyson's minimum weekly cost to still satisfy his dietary needs. So, how do we go about doing this? Well, as discussed in the last exercise, it's good to do a table to summarize all of the things that we need. So, what are we talking about here? Food, powder, one of them is Power Boost, one of them is Superlight. Conveniently, we've been told number of tins is going to be X and Y. So second column's done. Alright, so now we can look at the constraints that we've been provided. Power Boost has 30 units of carbs, Superlight has 10 units of carbs, and every week athletes have to have at least 170 units of carbs. Power Boost has 30 units of protein. Superlight also has 30 units of protein. Athletes have to have no more than 330 units of protein. So that no more than becomes important later. Use a different color here. Power Boost has 100 units of vitamins. Superlight has 200 units of vitamins. They have to have at least 1400 units of vitamins. And we've got another set of variables here that comes in later. The costs. Power Boost costs $5 each. Superlight costs $3 each tin. We don't have a cost to play with. We don't have a constraint for that, but that's because our objective is to find the minimum weekly cost. We're trying to minimize this objective function, which is going to be a linear one for the cost. Okay, so that'll come into it later. So let's finish off this table. Let's do carbs first. Carbs. Power Boost contains 30. Superlight contains 10. Protein. Power Boost contains 30. Superlight contains 30. Vitamins. Power Boost contains 100. Superlight contains 200. Cost. Power Boost is $5 each. Superlight is $3 each. And so now we have our table pretty much ready to go. We just extend it to get totals so that we can set up our constraints. So totals. Number of tins, X and Y, we don't know. That's what we're trying to find out, so just leave it. Carbs. They have to have at least 170 units, so greater than or equal to 170. Protein, they're not allowed more than 330. So instead of greater than or equal to, they're going to be less than or equal to 330 units of protein. Vitamins, at least 1400, so they need to be greater than or equal to 1400 in total. And the cost, we don't know, we're trying to minimize that, so minimizing it. Okay, so our table is done. Therefore, our constraints can be summarized like so. Number of Power Boost tins, I can't have negative of them, so it's going to be greater than or equal to 0. Number of Superlight tins can't be negative, so it's greater than or equal to 0. Total carbs constraint is going to be 30x plus 10y is greater than or equal to 170. Where does that come from? It comes from that column there. Total protein, 30x plus 30y is greater than or equal to, sorry, not greater than or equal to, they're only allowed to have up to 330, so less than or equal to 330. Total vitamins is going to be 100x plus 200y is greater than or equal to 1400. So there's our constraints. And before we start drawing the graph, we need to decide on an objective function. What are we trying to maximize or minimize? Objective function is the total cost, and it's going to be minimal as possible. So total cost is represented by the function $5 for every tin of Power Boost plus $3 for every tin of Superlight. So 5x plus 3y is the objective function, and we're trying to minimize that. So we now need to draw this simplex based on this. extremely accurately, because there is no way of finding the corners automatically on your calculator or anything. You just need to draw super accurately, so that you can see all of the points and the crossovers on the grid line. So I'm going to get a grid. Got a grid here, and resize it so it's big enough. Hopefully that's vertical. This video is going to be extremely long, but we'll deal with that. Okay, so there's my grid ready to go. Alright, need a ruler on this screen. It's going to move around everywhere, but we'll have to deal with that. So my y-axis there. X-axis here. So before we set up the scale, we need to know where our constraint lines are going to be crossing the X and the Y axis. So we need to do some setup there. Total carbs. So total carbs. The X int is going to be when Y is equal to 0. 30x plus 10 lots of 0 is equal to 170. 30x is equal to 170. X is equal to we need to work out what 170 divided by 30 is. So calculator time. 170 divided by 30. 5.67 to 2 decimal points. So 6 recurring actually. What's the y-intercept? Y-int is going to be 30 lots of 0 plus 10y is equal to 170. 10y is equal to 170. Y is equal to 17. So total carbs I'm going to do in blue. No, sorry, I'll do it in black. Total carbs crosses the y-axis at 17 and the x-axis at 5.67. So let's make it 2, 4, 6, 8, 10, 12, 14, 16, 18. So at 17, y is equal to 17. And at x is equal to 5.67. So 2, 4, 6, 5 and 2/3. So around there. So our first constraint is set up. First one down. That is representing the carbohydrates constraint. Second, we need the protein constraint. So total protein x int is going to be 30x plus 30 lots of 0 is equal to 330. 30x is equal to 330. X is going to be 11. Y int 30 lots of 0 plus 30. Y is equal to 330. that is going to be 11 as well. So the second constraint for protein is going to be 11, 11, 6, 8, 10, 12. So 11 and 11. So I can draw that one in now. This is going to be an extremely long video. It's alright, you're going to have to do this process yourself too. So at this stage, we've got two of the constraints down. We need the third one. Total vitamins. Total vit x int is when y is equal to 0, so 100x plus 200 lots of 0 equals 1400. 100x is equal to 1400. X is equal to 14. Y-intercept, 100 lots of 0 plus 200 y is equal to 1400. 200 y is equal to 1400. Y is equal to 7. So our other constraint here is y is equal to 7. X is equal to 14. 12, 14. I haven't made the best use of this graph line, but we'll manage. No, this grid we'll manage. Well, that's not the best line. It is really important that we draw these lines accurately because there's no algebraic way to find... Well, there is, but it's beyond our maths. There's no way of you using algebra to find the possible solutions. You need to see where it crosses the grid lines perfectly, and that's only going to happen if you've drawn your graph perfectly. That's better. So there's our constraints. Now, what can we colour in? Well, vitamins was greater than or equal to 1400, so we're talking about above this line. Protein was less than or equal to 330, so the protein was 1111. So it's under this line. So under this line, over this one. And the total carbs was greater than 170, and that line was this, so it's greater than that. So our feasible region is this area in here. Alright. So all of the dots in that feasible region on the edges are feasible solutions. So we've got one there, another dot there, another dot there. So all on the edges, on the corners, and any whole grid line crossovers are feasible solutions. There's another dot there, another one inside, another one inside the region, and there's nothing else there. So all of these dots equal feasible solutions. Now, to apply the simplex algorithm and minimize the cost, which is represented by the objective function of the cost, 5x plus 3y, we need to find the cost of each feasible solution combination and identify the lowest. This is applying the simplex algorithm. So how do we do that? We set up a table, feasible solutions, and the representation of the objective function, which is cost, which is 5x plus 3y. We tabulate that and find them. We find the result of those feasible solutions and find which is, in this case, the minimum, because we're trying to minimize the cost. So, the feasible solutions, we need to list them. This one is 3, 8. This one is 4, 7. This one is 5, 6. So can you see how important it is that you have drawn this accurately? This one is 6, 5. Otherwise you wouldn't see these crossovers. This one is 7, 4. And this corner one is 8, 3. We'll do this bottom corner here. That is 4, 5. And the inner ones, we've got 6, 4. We've got 4, 6. And this other inner one is 5, 5. So these are all the possible feasible solutions. We need to list them and find their costs. Oh, that's the worst line ever drawn. So, long process. You can see I told you it would be a long video. So, what do we have? 3, 8. 4, 5. 4, 6. 4, 7. We don't have any other 4 ones. 5, 5, 5, 6. 6, 4. 6, 5. 7, 4. And I think the last one is 8, 3. Please let this be correct. How many do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright. So now we can find the costs of those and find the minimum. So, 3 lots of... so what we're doing is substituting. So I'll show the first one in full. We're substituting this value of x and this value of y into the cost objective function, which is 5x plus 3y. So 5 lots of 3 plus 3 lots of 8 is going to be 15 plus 3 eighths is 24. 15 plus 24. 15 plus 20, 24 is 39. So that's one possible cost. 5 lots of, worst 5 ever drawn. 5 lots of 4, so substituting that 4 and the 5 plus 3 lots of 5 is 20 plus 15 is 35. So that's a lower cost, but we don't know if it's the minimum yet. We haven't gone through all the options. 5 lots of 4 plus 3 lots of 6, 20 plus 18, that's 38. 5 lots of 4 plus 3 lots of 7, 20 plus 21 is 41. So going higher again. 5 lots of 5 plus 3 lots of 5, 25 plus 15, 40. 5 lots of 5 lots of 5 plus 3 lots of 6, 25 plus 18, 43. 5 lots of 6 plus 3 lots of 4, 30 plus 12 is 42. 5 lots of 6 plus 3 lots of 5, 30 plus 15 is 45. 5 lots of 7 plus 3 lots of 4, 35 plus 12, 35 plus 12, 47. 5 lots of 8 plus 3 lots of 3, 5 lots of 8, 40, 49 I think, yes, 49. So what you will find here is that we have found the minimum cost is going to be $35, and it happens when X is 4 and Y is 5. So have we answered the question? Find Tyson's minimum weekly cost to still satisfy his dietary needs. Yes, we have found it. Therefore, Tyson's min cost is $35, buying 4 tins of, what was it called again? Power Boost. Tins of Power Boost. And what was the other variable? 5 tins of Super Light. And according to the Simplex algorithm, the optimal solution, the minimum or the maximum, always occurs at the corner of, or the vertex of the feasible region. Was that the case? 4 and 5? Yes, that occurred at the corner of the vertex, at the corner of the feasible region, the corner of the vertex of the Simplex. So that shows the Simplex algorithm at work there. So that was a long video, but that shows you the full process of applying the Simplex algorithm to maximize or minimize an objective, the objective being to minimize the cost of meeting the dietary requirements here. The dietary requirements set up all of the constraints. We found the intercepts for all of these constraint lines so that we could draw them on the graph accurately here, so that we could color in our feasible region, define where all the feasible solutions were, so that we could find the points and the coordinates of all those feasible solutions, which we could then apply the Simplex algorithm to by putting them into a table, finding the cost while finding the total value of the objective function using those feasible solutions, and finding the minimum or the maximum. In our case, we found the minimum, which was the answer to the question. So Tyson's minimum cost is $35 a week, having 4 tins of Power Boost, 5 tins of Super Light. So hopefully that helps you out, and I will see you on the next video.